Right up where we left off here. So I'm zooming ahead, jumping into chapter 22. So I'd kind of mentioned that this is the point in the semester where we jump around a little bit. So now I want to talk about collision theory. And so collision theory is picks right up where we left off on this mean free path and frequency of collisions. And it's a way that we can kind of predict what the fastest possible gas phase reaction should be. Okay. And as you might guess, it's based on, the distance, the average distance a molecule travels before it collides, as well as the frequency of those collisions. Okay. So we could think of this either for A plus B going to products or an A plus A going to products. Okay. So let's see, we'll just remind ourselves, right, with this reaction, both of these are second order reactions. But I'll just remind you, this one is negative K times A times B. And it would be the same rate if I said dB dt, right? And in this one, dA dt, this is going to be negative K times A squared. Okay. So, and if we really start to think, what is this rate constant? Is there something more fundamental going on? Okay. Well, that rate constant is going to be proportional to sterics. And what I mean by that is really the orientation of collisions. And we're going to call that steric factor. It gets a capital P. And we'll talk in a moment how we come up with that steric factor. There's our frequency of collisions, which we just talked about, right? That was our little z, okay? And then there's also this minimum energy requirement, okay? And we remember from our early discussions, this minimum energy requirement is related to the Arrhenius equation. So that goes as e to the negative EA divided by K Boltzmann T, or divided by RT, depending on our units, okay? And so speaking of units, let's talk about this frequency of collisions for just a moment, all right? So we notice here my frequency of collisions is sigma times C bar relative times P over KBT. So what is all of that? So remember, P divided by KBT just gives me my number density, right? It gives me my concentration of molecules in the gas phase. And so if you think about the way that these units work out, right? I have a K, and then I have these times those concentration units. So what I really need on my frequency of collisions is just simply sigma times C bar relative, okay? Because I'm gonna include that, that missing P over KBT, right? That gets included right here in those concentration terms, okay? So what if we have, so I'll write this in terms of the A plus A and the A plus B because they are just slightly different, okay? And instead of thinking of these as a rate, dA dt, I'm going to give this a big capital Z, and I'll write that as ZAB. So that represents my collisional density. And if you think about what a collisional density means, right, it's got the same units of this. So that's going to be molecules per cubic centimeter per second, okay? So now for the ZAB, so we're not going to include this orientation factor just yet. I'll build that in soon, okay? But that's going to go as sigma, okay, times my relative mean speed, 8 kBt, divided by pi mu all square root, all right? And then now we recognize that we're going to have this factor right here, this e to the negative EA divided by RT. And then, of course, there's going to be a times A and a times B, okay? And so if we inspect through all of this, we can really see that this gives us the rate constant K, okay? So what about if it was ZAA is what I meant to write, for an A colliding with an A. Well, that does change the relative speed just slightly because of this reduced mass. So that's going to go as sigma. And let's see, I've worked out the math already. That's going to go as 4 kBt divided by pi times the mass of A instead of that reduced mass, okay? And that's, of course, all square root. And then e to the negative EA divided by RT. And then, of course, all times A squared. So, and if we think about these units for just a minute, right? So we know our cross section is in, we'll just say, we can think of it as meters squared per molecule. And our relative speed was in meters per second. So you can see right there, that gives us a meter cubed per molecule per second. And that is the units of a second order rate constant, right? And then when we multiply this through by, it's going to end up being molecules squared per meter to the 6th power. We're going to get our proper units for rate, okay? So continuing along. So how do we deal with this steric factor? So I drew this picture here and left myself all this space, but I realized I probably didn't need this much space, okay? So we attempt to adjust this reactive cross-section, or really I should say, this sigma, right, that we talked about before. We can now start to think of this as a physical cross-section. And so by physical, right, let me back up to this picture, right? It's literally just based on the size of the molecules, okay? But we could readjust that and turn it into a reactive cross-section by including what we call the steric factor P. So that's the steric factor. And so this is a rather simplified kind of way of looking at this. But if you notice here, the way this works, if right here in this picture, this green circle is my physical cross-section, purely just based on the size of the molecules, then my reactive cross-section is, smaller than that because perhaps there's only one little region of the molecule where the collision needs to happen, right? So for example, I've been talking a lot about OH reacting with double bonds. I'm getting some crazy sunlight in here. I'm gonna have to close that window for the next video. That's weird looking, huh? Okay, so so we talked about how, for example, if I have some alkene and I'm trying to react an OH molecule, right? We know that it's going to react with the double bond, okay? So my physical cross-section might look something like this, but my reactive cross-section might only be something like that. And so really the only way that we can determine this is through experimentation, okay? So for example, let's see here. So we'll start to put this all together now. So we recognize K is going to be P times sigma, right? That's our reactive cross-section, times my C relative, so that's 8 kBt divided by pi mu to the 1/2 times E to the negative EA divided by K Boltzmann T. So I'm not going to go through the derivation for this, but recall, right, that comes from our molecular partition functions, okay? Well, look, this is our Arrhenius frequency factor, that A term that we talked about, okay? And so oftentimes it can be really challenging to know what that steric factor is. So that's why we often will rely on experiments, right? We do the experiment at several different temperatures, and we fit, right, natural log of K versus 1/T. And so that gives me, the slope equals the activation energy, and the intercept ends up being the natural log of A. So we get that frequency factor term. And usually we can calculate sigma and the relative velocity pretty well. So we kind of have to back calculate what that frequency factor is, okay? So what I also want to point out, what you're probably used to seeing now in your NIST, in the NIST Kinetics website, right? It gives the Arrhenius equation as something like this: A times some term. Oh, I should have had this in front of me ready to go. But it's usually A times some term divided by T raised to the n power times E to the negative EA divided by RT. Okay? And so that's because there are these temperature dependent terms. And in NIST, these are usually lumped together in some type of scalar quantity. Okay? And you're going to see that when you go to start looking up these reactions for your Kinetica project. Okay, so now how can we use this to calculate the fastest possible reaction? So here you can see on my Mathematica model, so I put in K, and I didn't worry about putting in the steric factor P, so we'll just assume it's 1 for now, which is a pretty reasonable assumption for small molecules. So that's sigma times C relative times this Arrhenius term. Okay, and so I've also wanted to be able to convert this into our convention, cubic centimeter per molecule per second. So here that calculates that, because when we go through and do this normally, as I showed, right, that's going to give us the meter cubed per molecule per second. And so this term right here, 100 cubed divided by 1, that converts that into cubic centimeter. And so you can see that it comes out to be 2.88 times 10 to the minus 10. And because this is all like, just estimating, we get that our fastest possible gas phase reaction should be something like 3 times 10 to the minus 10 cubic centimeter per molecule per second. Okay, so I know seems like a crazy small number, and it's hard for us to have some kind of a reference frame for that number. But now here it is, right? So in this calculation, I assumed an activation energy of 0. And with an activation energy of 0, that's going to give me the fastest possible reaction, which you can see in the cubic centimeter per molecule per second unit is about 3 times 10 minus 10. So we can also convert that into our standard liter per mole per second. And that turns out to be 2 times 10 to the positive 11 inverse molarity inverse second. Okay, so again, these numbers are really hard to have some type of a reference frame, but we can see now if we've got rate constants, second order rate constants that are about 10 to the minus 10 or even 10 to the minus 11, that's a really fast reaction, really, really fast, given that 3 times 10 to the minus 10 is the fastest possible reaction. Okay, folks,